Welcome everybody to my talk on computational aspects of full waveform inversion. In this talk, I would like to discuss a couple of different aspects of full waveform inversion. One is how to get over the nonlinearity problem using the multi-grid approach in the time domain. And the second is how to do implementation in parallel, both using MPI and CUDA. Let us review the procedure for full waveform inversion. The initial velocity model that may be obtained, for example, from tomography, is lacking the high-resolution details that produce the reflections. So when we predict data using this velocity, we don't predict all the reflectors that the observed data contains. So the difference between the observed data and the predicted data on each iteration, it will give us the information about the velocity model. This information can be mapped from the data space to the velocity space by using a simple migration. Now, one extra difficulty that happens when we solve these problems is that these residuals contain not only velocity errors, but also modeling errors and processing errors. So in real data full waveform inversion, we have to deal with all this mixed information. However, when we do synthetic data, the procedure is a lot simpler because we don't have modeling and processing errors. So that is, in particular, very important when we use the same engine to predict the data that we are going to use as our original pseudo real data and the predictions on each iteration. That's what we call the inverse crime. So in this presentation, I will try to do special things to eliminate that problem. Now, there are two different ways to implement full waveform inversion. You can do it in the time domain or the frequency domain. And in each case, you can analyze the computational cost dependency. In this talk, I will mostly focus on the time domain. And the reason is because the frequency domain is not that efficient for 3D surveys. So for the time domain, the computational cost can be traced to be proportional to the 6th power of the number of cells along each dimension. And this will be very important as we go to higher frequencies because finite difference requires to have finer grids to achieve higher frequencies, and therefore the number of cells along each dimension and has to be very much double every time you go to double the frequency. Right? So we will see that this is the fundamental reason why the computational cost grows very high as we go to very high frequencies. So let's see an example of how this works for a simple case of the Marmousi model in 2D. So we start with 40 shots that I generated in the true velocity model. And I start with the initial model that is smooth. And I do that in several iterations, in 20 iterations. We see that the energy of the error in the predictions is decaying to a fraction of the original, that it will be 1. Right? So as this is happening, the velocity model is achieving more and more resolution. Now notice that for doing this, I didn't need to go to very high frequencies. I only use a maximum of 8 Hz, which allow me to work with coarse grids, in this case of 32 meters on each side. And because of that, I could do this, for example, in a small cluster in very short time, in 5 minutes. One of the things that people are trying to do these days is to obtain very high resolution full waveform inversion, which it will provide us with detailed information equivalent to what we could obtain by doing migration. In other words, they are trying to replace the sequence of full waveform inversion plus migration with simple full waveform inversion. Now, to achieve this, the problem is that we have to go to a very to higher frequency, and also we need to use smaller cells, which increase the computational time. But another problem is that as we try to go to higher frequencies, we see a deterioration in particular in the shallow part, produced by the problem of nonlinearity. The problem of nonlinearity can be understood easier when we look at the different cost functions for different frequencies. So the cost functions that represent the mathematical quantity that we are trying to minimize, they can have complex shapes for nonlinear problems like this, and they contain a global minimum that is the solution we want, but also contain these local minima that are solutions that can trap the algorithm and prevent us from arriving to the global minimum. Now, the cost functions at low frequencies tend to be much more open. So if we start with any initial velocity that is located, for example, anywhere in this area, for the low frequencies, we still will achieve convergency. But if we start at a similar point for higher frequencies, we may get trapped in this local minima and therefore not being able to achieve the solution. Now, to deal with this problem of nonlinearity, typically what we do, we solve the inversion in stages. For example, we start with the smooth velocity model, and in the first stage, let's say that we want to achieve, we want to work with data up to 8 Hz, we can work with the coarse grid and obtain completely converge to the solution that is the best we can achieve for that range of frequencies. Then we take this velocity and interpolate it to a finer grid, and we use it as the initial velocity for the second stage, where, for example, we can go double the frequency, in this case going to 16 Hz, where we see that now the resolution is higher. Right? And then we repeat this to go through the next stage, and in each stage we can achieve better resolution. So for example, here we have a similar multi-grid application for a different model. Right? We see here the initial model, the first stage up to 8 Hz, right? Then using that as initial model for the second stage up to 16 Hz, and then the final stage up to 25 Hz, where you see that we have gotten very well all the little details of the model. So what happens if we try to achieve the same high frequency result, but in one go? Well, here we have the example for the Fuchs model, and here is the initial velocity model. We see that if we try to go all the way to 25 Hz in one go without the multi-grid approach, we get a severe distortion of the structures that are produced mostly for these local minima at high frequencies. On the other hand, if we do this in the multi-grid approach that I showed in the previous slide, then we see that that doesn't happen, and we recover all the fine structures. Now, the results I showed before, although they are very good results, they rely on the inverse crime. And the reason is because for that case, for those results, I predicted the data, what I call observed data, on the same grid where I was doing the inversion for each stage. Of course, that is not what happened in reality, where we have one data set that is acquired at a particular frequency, and we have to adapt that data set to every stage by applying some kind of unpass filter. Applying a bandpass filter to the input data is no big deal, but a first naive approach to this reveals some interesting deterioration in the results. And that is produced by the fact that when we apply a bandpass filter to the high frequency data, we change the shape of the wavelets. And in addition, the artifacts that are produced by generating the data in a fine grid are different from the artifacts we get when we generate the data in a coarse grid. So these differences illustrate how the inverse crime scenario makes the inversion significantly easier than is in reality. So this tells us that we have to be very careful on how we change the frequency of the data. One way that I am doing in this work is I'm applying a shaping filter to change the frequency of the input data to the frequency of the predictions. Now notice that this matching filter is not being applied to the prediction data to match the observed data because that wouldn't work, because it means that we will have to predict frequencies we don't have. Instead, this matching filter is applied to the input data to match the predictions. Right? So when we do that, we can now compare the predicted trace with the modified input trace. And you can see why when we apply the simple bandpass, it didn't work, because there are many differences in the resulting trace. So that is why the shaping filter in this case is a better choice. Now, in practice, I found that even the shaping filter is often not enough. So often we have to apply a vertical shift, and that can be obtained by using a simple cross-correlation between the predictions and the input data. This cross-correlation just perform minor shifts. You can see here that the magnitude of the shifts are just in the order of very few samples. And now we see if we apply this in the sequence, right? We can see the progression from each stage as before. Although the results are not as good as when doing the inverse crime. We'll see a further improvement in this in a few minutes. Now, what is the problem with this approach? Notice that even when I am using a quite efficient MPI implementation of this process, where I am parallelizing the data across the nodes, so in every during the inversion, I can reduce the computational cost almost linearly with the number of nodes. Still, what happens is that as we go from one stage to another, we have to reduce the cells by half in each direction. And in 2D, that is a factor of 4 times. In 3D, is a factor of 8 times more computational cost. If we do that in addition, we have to add the extra computational time for the time step. Right? So we have an increase of 8 times in 3D and 16 times in 3D. Right? So it's in this example, for example, in 2D, I start with 5 minutes, 20 minutes, and 1 hour, 20 minutes. So as you see very quickly, if you're doing this in 3D, becomes very, very difficult. One solution to this problem of the computational cost that people in the industry have been applying for at least 10 years is to move from the CPU model, right, where we basically apply more processors to solve the problem, but each processor is very intelligent, to the GPU model, where also we use many processors, but each of them is not very intelligent. Actually, it's very cheap. So instead of parallelization on 10 nodes or in 100 CPUs. In the GPU model, you can parallelize thousands of times, 2,000 times or so, and each of these processors that is doing the work is very very simple. That is a different philosophy. So in practice, people use a combination of the two models. So for one side, we have a cluster where we have different nodes, and each node has a multi-core processor. In addition, each of these nodes has a GPU. Right? So typically, when we do this kind of combination of the two HPC models, we can have around, let's say, hundreds of CPUs and several thousands of threads for the GPU working simultaneously. Now, a difference of other parallelization techniques, this programming requires to understand the hardware. And so it's not easy. Typically, experts will develop different patterns, programming for different problems. And the rest of us, we basically find when we find a pattern that matches something we're trying to solve, we use it. And that's the particular case for finite difference, right? So the problem of explicit finite difference that we use for modeling is equivalent to a convolutional pattern, which is highly optimized in GPUs because it's also used in computer vision for convolutional neural network. So this pattern achieves very high speeds, order of, let's say, 2 orders of magnitude. But to do that, you need to use a particular very small memory. It's called the shared memory, and that requires a major re-engineering of the code by using very small windows that overlap in the model space. Now, the efficiencies achieved with the GPU, they become more and more interesting as we go into more complex operations. For example, if we increase the order of the finite difference, right, we can see that if we do that in CPU, either using the shared memory model of OpenMP or the distributed model of clusters using OpenMPI, we see in both cases the computational cost increases practically linearly with the complexity of the calculation. But when we do that in the GPU, the computational cost, it becomes fairly constant even when we are doing significantly more computations. And not only that, when we go into, for example, 8th order, we see an improvement of in the order of 100 times compared to doing the same operation using an OpenMPI distributed model. Now, this interesting effect that we can increase the complexity without increasing the computational cost also extend to other parts of the implementation, for example, boundary conditions, or when we go from acoustic to elastic. So it's because of the resources, the number of resources in the GPU is larger than we normally use. It happens that when we increase the complexity, for example, in this picture going from a sponge boundary conditions to PML, the computational cost in the CPU increases double for the CPU, but it remains fairly constant for the GPU. So in some ways, it's like achieving a superlinear scaling, and the reason is because the threshold at which the computational complexity affects the computational efficiency is much higher than for the CPU. So now using these CUDA implementations, we can see the results with the multi-grid approach. They are very close to what we obtained before with the inverse crime, but this time we eliminated the inverse crime by working with different grids. It's interesting that the results here for the CUDA approach are slightly better than the ones that I showed before for GPU, and that's something that happens because the engineering behind the two implementations, they diverge. They can not be exactly the same because of the way that CUDA requires dividing the model space in small windows. So here we see again the multi-grid CUDA results for the foothills model, where we see that we get a very nice resolution, quite close to what we saw early on for the inverse crime. So let us summarize some of the key ideas that we have seen in this talk. First of all, when testing full waveform inversion algorithms, it's critical not to fall into the inverse crime. And one way to do that is to work with multi-grids in the time domain. Because by changing the grid size, it helps to destroy some of the artifacts that help to do the inversion in the inverse crime scenario. However, this also requires some kind of adaptation between predictions and input data. The time domain, FWI, is very efficient either in 2D or 3D because it permits coarse grain parallelization. So even in a small cluster, you can get gains in the order of 20 times. Frequency domain, on the other hand, is not as efficient in MPI parallelization because it requires clusters with fast communication across nodes that tend to be much more expensive. And the GPUs allow us to run very fast time domain finite difference, but they require careful programming with CUDA and definitely needs to use shared memory. In these conditions, you can easily achieve gains in the order of 100 times. So to finalize, some acknowledgements for support to cruise sponsors, a Canadian SEG, and NSERC. And in particular, thanks to Peli and Yang for many useful examples in Madagascar, and Sam Gray for useful discussions.